Glycolysis. In this video we're going to have a brief overview of glycolysis, molecules involved, the enzymes involved, ATP use, ATP production. Should be noted this video mostly has to do with bacterial glycolysis, so if there's some variations, which there may be, in this video mostly pertains to bacteria. For step 1, we have glucose being converted to glucose 6-phosphate, and that's via a hexokinase. So hex being 6, kinase usually adding a phosphate or removing a phosphate group, and that's going to use one ATP molecule. So the phosphate's going to be coming from the ATP molecule. So we have glucose using hexokinase to add a phosphate to itself, and you get glucose 6-phosphate. The next step, once we have glucose 6-phosphate, you're going to see glucose 6-phosphate via phosphoglucose isomerase converted to fructose 6-phosphate. So again, you have an isomerase which is going to create an isomer of glucose. So that moves glucose 6-phosphate to fructose 6-phosphate. The next step, we have fructose 6-phosphate being converted to fructose 1,6-bisphosphate, and again, this is via a kinase. In this case, it's phosphofructokinase. So again, kinase adding a phosphate group. So you have ATP, and that's the source of the phosphate. ATP being converted to ADP to make fructose 1,6-bisphosphate. Once we've created fructose 1,6-bisphosphate, we're going to look to create glycerolaldehyde 3-phosphate. And this is done via the enzyme fructose biphosphate aldolase, which is essentially cleaving the fructose 1,6-bisphosphate in half to create glycerolaldehyde 3-phosphate. It should be noted that in this process, glycerolaldehyde 3-phosphate can be converted to dihydroxyacetone phosphate via triosphosphate isomerase. And you can see the difference in the picture there, glycerolaldehyde 3-phosphate, dihydroxyacetone phosphate. For this video, we're just going to focus on glycerolaldehyde 3-phosphate for the time being. Now, that last process we talked about creates 2 glycerolaldehyde 3-phosphate molecules. So the rest of the process here will actually occur twice. So glycerolaldehyde 3-phosphate is going to next be converted to 1,3-biphosphoglycerate, and that's done by glycerolaldehyde phosphatase dehydrogenase. And here you're going to see NAD+ receiving a hydrogen molecule, and it's going to be a dehydrogenase reaction, so it's the loss of water. And that takes glycerolaldehyde 3-phosphate via glycerolaldehyde phosphate dehydrogenase to 1,3-biphosphoglycerate. So once we have 1,3-biphosphoglycerate generated, we're going to try to create 3-phosphoglycerate. And this is done by a phosphoglycerate kinase. And this time we go 1,3-biphosphoglycerate to just 3-phosphoglycerate. And so we have the generation of an ATP. And again, phosphate's involved, so the enzyme is going to have the word kinase, which has to do with phosphate transfers. So we have phosphoglycerate kinase facilitating 1,3-biphosphoglycerate, converting it to 3-phosphoglycerate with the generation of an ATP. Once 3-phosphoglycerate is formed, phosphoglycerate mutase converts the molecule to 2-phosphoglycerate. I think the enzyme's name is mutase, so it sort of mutates it, moving the 3-phospho group to the second carbons to create 2-phosphoglycerate. Once 2-phosphoglycerate is created, we have a dehydrogenase reaction, and that's facilitated by enolase, which converts 2-phosphoglycerate to phosphoenolpyruvate. And once we have phosphoenolpyruvate, again we have pyruvate kinase coming in, or not again, but a kinase enzyme, so it's going to generate another molecule of ATP via the removal of the phosphate group from phosphoenolpyruvate to create pyruvate.